Okay, so um, okay, what I'm going to do is sketch over here on the right a figure of pressure versus the amount of the volume that's liquid. Okay, so it's the volume percentage that's liquid going from 0 to 100%. And I'm going to sketch that figure at 4 different temperatures: a low temperature, a higher temperature just less than the critical, a yet even higher temperature just above the critical, and then the highest temperature, T4. And just so you get a feel for what these so-called liquid volume curves should look like. So if we take it temperature 1, that's got a bubble point over here, about right there. So this is the bubble point at temperature 1. I'll just call it PB1. And if we lower the pressure into the two-phase region, we'll hit 90% there, and then it'll hit 50%, and then down to 10% at sufficiently low pressures. So this is going to be, well, let's see here. I don't want to make this maybe too accurate, but let's see, 10 volume percent. I'm going to put here. That's about right there. Let's see, 20% there. 50% about there. So it's more or less something like that. Almost linear, the way I've drawn it at least. Then we'll go to the higher pressure, T2, closer to the, it's got a higher bubble point right here. So that's going to be right there. That'll be bubble point at temperature 2. And this one's going to have more curvature. I'm not going to look it off of this, but this is going to have a little more curvature, something like that, going down like that. And then as we go to temperature 3, at this about the same saturation pressure, just a bit higher, so it'll be maybe right here, we've got a dew point, and that's at the 3rd temperature, so I'll just call that PD3. And it will reach a maximum percentage of liquid of about, that's right, 20, so that'll be something like that. And then at the highest temperature, T4, the maximum was about 13%. It starts at a slightly lower dew point here, PD4, temperature 4. You can see it's a little bit lower than the dew point at the 3rd temperature, and it doesn't go as high. So this is going to go up to about 13%, turn around, and then come back down, something like that. And So the final curve I'm going to show is if we had taken at the critical temperature. Okay, and at the critical temperature, it's going to be, the pressure is somewhere between those. So it's going to be something like this. That would be at the critical temperature. It could either come, if you just went a little bit less than the critical temperature, it would come from the oil side, and if you went just a little bit to the right of critical temperature, it would come from the dew point side. But it would basically grow very rapidly towards 50%. Okay. So I'm going to sketch this one here in green, in red, because it's kind of coming from the gas side, kind of like that. And then if it came from the bubble point side, then it would basically go down like that. Follow the same path down here. Okay. Didn't do a very good job of that, covering that, making that green.
You're saying the intersection of both should be on the 50%?
Well, about 50%. That's what it looks like. It goes quickly down to 50%. So it's going to be something. It doesn't have to be 50%. It could be 40 or 60. But it's going to be, if you come just from a little bit to lower temperature, it'll come from the right. And if you go from a little bit higher temperature, it'll come from the left. But essentially, it'll have the same percentage oil volume at any given pressure almost throughout the pressure range, whether it's originally reservoir gas or originally reservoir oil. So the point here is that this is defined formally as a reservoir gas, this is defined formally as a reservoir oil, but what you see is that through the great majority of pressure below the saturation pressure, it's behaving exactly the same. Okay? Doesn't really, there's a very limited range of pressure where it's got a different oil and gas volume percentage. Okay? Any questions about that? So this is a phase diagram only in the sense that it marks the boundary. This would be PB1, PB2, so it's not really a phase diagram per se, but it does give kind of the nature of the two phases within the two-phase region. So it's the alternative to having these constant lines of pressure. The constant lines of percentage liquid. This is just a different way to represent the same information. And you may see it one way or the other. Okay? So, the next phase diagram that I want to talk about, I think, is what's referred to as a ternary diagram. And it's usually used only in connection with where you injected gas into an oil reservoir. Okay? It's about the only time you'll see it used. Ternary diagram. You could say typically or maybe only used when you inject gas into an oil reservoir. Okay, but you know, it's used enough that I feel like we have to at least touch on it briefly. By ternary, that means 3. So what we're going to do is that we're going to take these literally hundreds, if not thousands, of compounds, okay, and we're going to kind of translate that into 3 pseudo components. If I could spell. Pseudo components. By the way, in petroleum engineering, you're going to see the term pseudo used a lot. Pseudo relative probabilities, you know, they've got pseudo for everything. And it kind of basically means it's not the real thing. It's kind of. So we're talking about the kind of components. Okay, in this case, we're going to take what's literally hundreds or thousands into 3 components. So we're going to have a light component, what I'll call L, for light component, I for intermediate component, and H for heavy component. Okay? Typically the light components would be methane, nitrogen, I don't know. Intermediate could be CO2, C2, maybe through C4, C5, I don't know, C4, C5, something like that. And the heavies would be C5 plus or C6 plus, something like that. Okay? Just lump them into 3 categories. Basically by boiling point. You just kind of and the ternary diagram applies at a fixed pressure and temperature. Okay? So let's go up to the plot here and just pick, I'm just going to pick arbitrarily this point here to look at our ternary diagram. Okay? At that pressure and temperature. I got 50% of each. Okay? I could pick anywhere on the curve, but this is, okay. And so this mixture is actually a, if we looked at the volume inside some kind of container, you'd have vapor and liquid, or gas and oil, as you want to call it. And the composition of the gas we would call YI, and the composition of oil would be XI. I realize I'm starting to write so small I can't even see it, but I'm trying to write clearly enough that you can make it out. So basically, we're going to look at a plot of the compositions. The total composition is ZI. The equilibrium gas composition is YI, and the equilibrium oil composition is XI. All right? But now we're going to use just the 3 components. And because we have 3 components, we can actually do a graphical representation of this, and I'll try to do this using what's called a ternary diagram. And I'll label it light, intermediate, and heavy. So if I plot a point at the top up here, what that's saying is that that's got 100% on a molar basis typically. I'll just 100 mole percent light component, light pseudo component. Down here we've got 100%, again on a molar basis, intermediate components, basically, intermediates. And over here we've got 100% on a molar basis, heavies. Okay. And for the sake of, just drawing something, I'm going to put this is going to be our ZI. That's the total composition for this diagram we did above. So it's got, in this case, it's got, well, to find out how much light you have, you kind of, along this line here, I'm going to take that away. It's 100% here, it's 90% there, 80% there, 70 and so forth. So I'm going to say it's like maybe 30% light. Okay? So from this, Z light is around 30 mole percent, kind of by eye. That's the way you kind of figure it out, is you draw the lines perpendicular to. So for the heavy, it's, you've got, if you, I don't know, it's about halfway between here and here, not quite. So maybe it's got 55% heavies. And then that would, of course, by difference, you'd have to have, help me, 15%. It's probably not right. 15 mole percent intermediates. Okay? Doesn't quite look right, but it's got to sum to 1, right? 100%. 25. Let's see, 85. Maybe this should be 45 on the heavy. Okay. Something like that. If I was a great artist, I would be drawing this isometrically correct and everything would be clear, but something like that. Okay. Now, the equilibrium oil composition up here, Xi, and the Yi, we're also going to plot this on the figure here. Yi and Xi. Okay? And there should be a straight line joining all three of those compositions. Okay? And this line here is called a tie line. It joins the equilibrium gas, Yi, and the equilibrium oil, Xi, and the total mixture, Zi. Okay? And I'm going to sketch down here. This is Zi. We've got 50% Yi, and on at least on a volumetric basis, 50% oil. Okay? Now, nature is such that if we were to take away 90% of the gas, okay? If we were to take away 9% of the gas, so that it looks something like this. Okay, we have Xi, and we've got just a little bit of the Yi left. Okay? If we did that, if we had a container, and we were like doing a magic show, and you could see the gas and you could see the oil, and we put like the magician does, slices the woman in half, or slices it, so that you get rid of the top part of the gas. So what would happen is that nature wouldn't wake up. Nothing would change in terms of the equilibrium of the system and what's left. Okay? because the energy of methane and the gas is the same in the left and in the right. It doesn't matter how much of that gas there is, as long as the gas composition is unchanged, then it doesn't matter. So this is an identical state of equilibrium. Mother Nature doesn't even wake up, doesn't know anything's happened. You've lost some things, but there's no need to start moving components around to re-equilibrate. Okay? We could do the same with the oil. We could say, well, let's just keep a little bit of the oil. And all of the gas. Okay? Again, Mother Nature wouldn't wake up. Equilibrium is the same. And if we call this Z, this has got a new Zi, it's a new total composition. We're going to call that B, A. And this one we'll call B. Then the total composition of A is going to be right here. And B is going to be up here. And it's going to be on the line as well. Okay? We can also take away all of the oil except one little drop. Or we could take away all of the gas except one bubble. Okay? And this I'm going to call Zi vapor. All that's left is vapor, and Zi liquid. Okay? Well, that's this point here. Zi vapor is this point here. That's equal to Yi. And that Zi liquid is just equal to the oil composition. So you can have any infinite number of total compositions Zi between Xi and Yi in any ratio you want to keep. And Mother Nature doesn't wake up. The equilibrium of the system remains unchanged. The methane chemical energy is the same. Okay? Nothing changes. But the total composition has changed. And that's the characteristic of this tie line, is that the chemical energy of the system doesn't change, but that the same equilibrium is always achieved with Xi and Yi filling the container in different amounts. So all of these have identical chemical energy. Both total and each component's chemical energy in either the vapor, which would equal the chemical energy in the liquid. And it's independent of how much vapor or liquid you have.
What is this? What's that? This concept?
What is the what?
Is it mu?
It's mu. Chemical energy is written mu, like viscosity, unfortunately. Yeah. But it's usually got the component I. I don't even know what this subscript here is. I forgot what I wrote here. Total. That's total. The total energy, if you take all the energy of all the components together. Okay. But, huh?
So for the Zi,
Yeah.
we know it's 30%. So we put it in the ternary diagram at the point 30%, line 30%. What about Xi and Y?
Xi and Y are fixed. These are the endpoints of the line.
Okay.
So here, Zi is equal to some fraction that's vapor. We usually call this fraction vapor. We can write fraction vapor. So that would be the moles of vapor over the total moles times the mole fraction of yi plus 1 minus vapor fraction. So this would be moles of liquid over the total moles times this, okay? So the value of FV for these different systems, this might be, I don't know, the way I've drawn it, it would be about maybe 0.4 here. The vapor fraction maybe 0.4 originally. This one here would be maybe 0.05. There's just a little bit of vapor. The next one might be 0.95. There's a lot of vapor and just a little bit of liquid. This one is basically 1 minus epsilon. It's almost all vapor, but you got one little drop of liquid. And the last one would just be you got an epsilon amount of vapor. So this equation applies along the tie line. It basically defines the tie line. Okay? I think it's called something Lever's rule or something. I don't really know what that means, but Lever's rule. You can look it up. Okay. So this is one way to use a ternary diagram. It's kind of, you're now just getting an orientation. It's just a way of plotting compositions at a fixed pressure and temperature. But you can also use this as a phase diagram to identify which compositions are single phase and which compositions are two phase. We can also do that. I'm just going to draw a picture now. We're doing cartoons, okay? Okay, because what we can do is that we can draw the line where Zi is equal to Xi, okay? I'm going to draw this line is where Zi is equal to Xi. One point is right there, right? So this line will typically look something like this. And it'll stop there. And then I'm going to take and draw a line where Zi is equal to Yi. And that's typically going to look something like this. Make it consistent with this one here. Needs to go through this point here. It's not a very pretty picture. Let me just make this a little bit different. Stops there, and then I'll let this oil stop there. Okay, something like that. So anywhere along the green line, you have something like this. So this is on the green line, and here the pressure happens to equal the bubble point, because there's just a bubble there, right? And for the situations like where you're on the red line, the pressure of the system is equal to the dew point. So we call this the dew point line. We call this the bubble point line. And inside here, everywhere inside here, we have two phases. Everywhere inside that envelope. And everywhere outside, we have single phase. Everywhere outside that envelope.
Question.
Yeah.
It's a constant temperature and pressure, right?
Right.
So what would make Zi moves?
You're changing the composition. You've got three containers. Okay? I basically go into the lab and I say, I want the lab, I've got a 1,000 component mixture, but I want the lab to distill off only the C1 nitrogen into one container. The middle container is going to have all the components from C2, including CO2, C2, down to C5. All those components, put it into second container. The third container is all the heavy C6 and heavier stuff. And then I just go into the lab and say, make 1,000 different mixtures, but keep the same pressure and temperature. And tell me if it's single phase or two phase.
And it's the same components. You're not adding any
No.
additional.
The only way this diagram is correct is if the heavy is always the same heavy. The intermediate is always the same intermediate. Same distribution of C2 through C4. Okay? And then you'll have a unique, at this pressure and temperature, you have a unique curve, the red line, the green line, and this point here is actually representing a critical point. Okay? That mixture is at its critical point. Okay? If we took this mixture composition and we did the lab, made up that pressure temperature diagram for that particular composition, right there, it would have some funky phase diagram like Curtis, okay? And they would find, I don't know what it's going to look like, they would find a critical point here. That critical point is the pressure and temperature we're talking about here.
Defects.
Okay? That's the pressure and temperature we're dealing with. It would have its critical point there. That particular composition. Every composition in this, every point on this diagram will have a different pressure temperature diagram. Okay? Okay? If we took we already looked at this pressure temperature diagram of that. That's up here, right? And the pressure and temperature we're looking at, I'm going to call this P star and T star. Okay? So this is P star and T star, and that's P star and T star. Okay? But for that particular composition right there, its critical point on its PT diagram is equal to that pressure. Okay? If we took this gas here, okay, if we took this equilibrium gas that we originally found, its pressure temperature diagram, I'll draw that in red. I'll mark P star and T star. It would look something like this. It would have to go through that point. And then it would have a critical point out here. I'm sorry. Its critical point might be down here somewhere. Okay? That's for the composition YI from the original. And then the oil, if we took that original oil that we had in the cell down here, and we did its pressure temperature diagram, its critical point might be here, and the diagram looks something like that. Okay? It's at its bubble point here, and every composition has its own pressure temperature diagram. Okay? In this composition map, the ternary diagram, if the composition is along the green line, then that composition is at its bubble point. If it's along the red line, the composition's at its dew point. If it's a composition inside, then it's two-phase. That means the pressure temperature diagram has to look something like this, where P star T star is inside the diagram. Okay? And that one special composition here, where the dew point line meets the bubble point line, that's a critical point. So that composition, if you draw its PT diagram, its critical point will be P star and T star. I suspect that to really understand this, you're going to have to probably review the lectures a few times. It'll ruin your Netflix viewing this weekend, I suppose, if you're really interested in this. It's not trivial, it's not intuitive, but it is kind of what it is. Okay?
Does it matter whether you're injecting, let's say, methane versus
We're not injecting anything yet. What I said for this diagram up here that I made is that so far we have three containers. We have the light container, which has got a certain distribution of C1 and nitrogen. That was all we put in the light component. In the original mole percent, the original composition ZI, maybe this was 72 mole percent and this was 8 mole percent. Okay? Okay. The intermediates, we had a container of that, and that was C2. Maybe it had 8 mole percent down to normal C4, C5. Actually, C5 I think is what we put. Normal C5. Maybe had 1.5 mole percent in a certain distribution. And then the heavy stuff, we had another container, and the C6 was, 2.3 mole percent, C7, 2.1 mole percent, C36 plus, 1.4 mole percent, something like that. And we just mix these three containers together in different proportion, in different amounts, okay, to create the whole map. That's what we made the assumption on. Then the ternary diagram has some meaning, some physical meaning, okay?
This diagram, do we find it experimentally? Or?
Yeah, that's what we started with. We just took our original mixture down to P star T star. And there's two phases. You look at the gas phase, measure its composition in the lab, that's your YI. So then we can plot that here. Okay? And the XI you get from the oil composition. Okay. Now we have a problem in this ternary diagram. we created this diagram by mixing together the lights and the intermediates and the heavies in just different proportions, right? To map the whole thing. But the problem is that if we look at the composition of yi, light component, so this is our zi. If we looked at our yi for the light component, C1 and nitrogen, this might be, I don't know what it's going to be, but 92% and 8 more percent. I shouldn't make it 8. It looks like I'm something like that. Okay? In the gas phase, it doesn't have the same relative amounts. It's not the same light component. It has a different molecular weight in the gas. And if I look at the oil composition in the real system, this might be 0.2 and 16 or something. Maybe not 0.2, but 3. I don't know. Okay. So the ratio is not the same. It's not the same pseudo component. Okay, and that is a problem. You're not really. The pseudo components are changing. Okay, so that's why this method is an approximative. It's a kind of a guideline. It's so basically this is violating that the 3 components, in our case pseudo components, are not the same. Okay? Each point that we have is not the same. And because you're violating that, there's a limit to how much you can use this quantitatively. Okay? It's kind of a and because of that, the ternary diagram can be very misleading. If you try to use it quantitatively. Okay? By quantitatively, you don't understand. But if you really try to use it in engineering, you can get in trouble. Okay? Because you're violating from the get-go. Because you have hundreds or thousands of components. This light component is going to change all over the map. It's not going to remain in a certain proportion. And the heavies certainly are going to look very different in the gas than in the oil phases. So you have to be very, very careful. And some of the smartest individuals in our industry have been tricked. In fact, the entire oil industry was tricked by the ternary diagram until about 1986 in understanding how gas can displace oil efficiently. Till 1986, because they used the ternary diagram religiously, they just didn't get it. They didn't understand what was really going on. And only around 1985, 86, there was a guy who came along and says, we can't use this ternary diagram. We have to look at all the components and study the mixing of injection gas and reservoir oil, not with the ternary diagram, but in some other way. So basically, the concept of developed miscibility, which we're not going to talk about in this course much at all, developed miscibility, And what we mean by that is really a very high, near 100% recovery of oil by an injection gas. Okay? And this fella in 1985, I think it was the paper, 86 maybe, his name was Aaron Zick. He kind of broke the industry's back by abandoning the Ternary diagram, studying the problem as a real problem within dimensions, meaning 1,000 components, you use all of the components, or many components, more than 3, to study how does gas recover the oil. Okay? Because the laboratory says you're getting 100% at 4,000 pounds. If you inject gas at 4,000 psia, you get 100% of the oil. Okay? But the calculations through the ternary diagram says that it takes 6,000 pounds to develop miscibility. Okay? Why was this inconsistency there? It had to do basically with the fact that the ternary diagram is dangerous to use quantitatively. So, okay, so that we'll stop at that.